You go through a tutorial that steps through aspects of detecting extrasolar planets through the Doppler motion of their parent star. And a lot of these ideas carry over when we would think of spectroscopic binaries, so detecting two stars in a binary system due to the Doppler shift. This is a little bit different because we're only going to get basically light from the star. We're inferring the extrasolar planet, which it just has a relatively small amount of reflected sunlight or starlight coming off of it. We're inferring its motion based on the motion that it's inducing in its parent star. We're not picking up an actual Doppler signal or a spectral signal from the planet on its own. All right, so we have two different views of the same extrasolar planetary system. Both objects are orbiting about their common center of mass. The star being more massive is closer into the center of mass, and the planet being less massive is further away. But they're both executing orbital motion with the same period, but since their masses are different, their semi-major axis is different. If this were our own solar system, then this point of the center of mass would basically be over on the surface of the sun. And so for the Sun-Jupiter system, Jupiter is most of the mass besides the sun in our solar system. So Jupiter executes its orbit at 5 astronomical units, and at the same time, the sun is going to roll around a point on the surface of the sun. So that's a top-down view of our extrasolar system, and this is close to side-on view. And this is the geometry we would think of for detecting a extrasolar planetary system through the transit technique, where this extrasolar planet is going to pass in front of its parent star and block out at least some of its light. And then half an orbit later, then the star is in front and the extrasolar planet is behind, and we would be missing the reflected light from that extrasolar planet. All right. Figures 1 and 2 show the orbits of the same extrasolar planet and star from two different points of view. We have a top-down view and then a nearly edge-on view. All right. As an extrasolar planet orbits around a star, the gravitational attraction between the two objects causes the star to make a small orbit around the system's center of mass. Which object travels in the largest circle? Well, the planet, having less mass, is in the wider orbit. Which object takes a greater amount of time to complete one orbit? And they both take the same amount of time. They have the same period. All right, at the instant shown in figure 1, which direction is the extrasolar planet moving? All right, so the extrasolar planet in figure 1, it is moving down the page, so toward the bottom of the page. All right, question 4. At the instant shown in figure 1, which direction is a star moving? The star at that instant, its velocity is pointing up the page, so towards the top of the page. In general, how does the direction the extrasolar planet is moving compare with the direction that the star is moving? This is one of the first things we want to wrap our mind around, is that they are always moving in opposite directions. If the planet is moving left, the star is moving right. The planet is moving down the page. The star is moving up the page. Their direction of motion is in opposite directions. All right, figure 2 shows the extrasolar planet and star from the side, or as seen edge on. With the instance shown, what direction is the planet moving? Okay, so I'm taking this and I'm rotating it, so I'm looking at it edge on. So in the edge on view, the planet is coming towards me, so out of the page directly toward you. All right, we have our two students again. Two students are having a discussion about the relationship between the movement of the central star and extrasolar planet and the Doppler shift of the light coming from the star. Student 1 says, since figure 2 states as the extrasolar planet is moving out of the page directly towards us, then the light from the star we observe will be blue shifted. Student 2, I disagree. The light from the star will be red shifted because the star is moving in the opposite direction the planet is moving. So, do you agree or disagree with either or both of the students, and why? So in this case, student 1 is okay up until that word. If the planet is coming towards us, the star has to be moving away from us because their motions are always in opposite directions as they're executing their orbits. And so therefore it should be a red shifted light. Student 2 is correct. Student 2 is on the ball again today. All right. Would the light from the star in figure 1 be blue shifted, red shifted, or not shifted? Explain your reasoning. All right, so this is a subtle question, but it is important. One of the main reasons for this tutorial. The star, if I am seeing it viewed from above, all of the velocity for the star is always in the plane of the sky. I will never detect a Doppler shift from it. If I have a edge-on solar system that we're observing, then I see as much of the motion of the star as I can. If I have a face-on solar system, you'll never detect the motion because it's always in the plane of the sky. No part of the motion of that star is along my line of sight. So this is not shifted, and Y is not moving along our line of sight, which is one of the limitations of using the Doppler effect to infer motion. You're never going to get the full motion of an object unless it is entirely along your line of sight. All right. Question 9. Would the light from the star in figure 2 be blue shifted, red shifted, or not shifted? Explain your reasoning. So at this moment in time, the planet is coming towards us and the star is moving away from us, and moving away from us is red shifted. If you are unable to detect any Doppler shift from a star in an extrasolar planet system, how must this system be oriented with respect to your line of sight? Explain your reasoning and include a drawing to illustrate your answer in the space below. So how must it be oriented? It must be perpendicular. Or you could say you're seeing it face on, which I'm not going to draw it again, but it's basically figure 1 again. question 11, which I'm going to go through something about the amplitude of the Doppler shift before we get to the next question. So, the amount that the light from a star in an extrasolar planet system will be Doppler shifted depends on the mass of the star, so that's capital M substar, the mass of the planet, lower m, subplanet, and the distance, d, between the star and the planet. And this relationship can be written out as the amount of Doppler shift proportional to the mass of the planet, inversely proportional to the square root of the mass of the star, and inversely proportional to the square root of the distance between the planet and the star. So you get the biggest signal for a high mass planet, low mass star, and they are close together. So I need to make mass of planet big, mass of star small, and the distance between them small. Figure 3 below shows 4 different extrasolar planet systems, A through D, and we're going to use this figure to answer questions 11 through 16. So we just step through these quickly so we're all on the same page. In case A, I have a massive planet that's just 1. It is at 2D, and the star has a mass of 2 m star. Case B, I have a heavier planet, so it's 2 mass planet. I have a smaller distance of 1d, and I have a lower mass star of 1 m star. Case C, I have the heavier planet, 2 times mass planet. I have the larger distance of 2d, and I have a smaller mass star of 1 m star. Case D, I have a lower mass planet, 1 m planet. I have the larger distance of 2d, and I have a 1 mass star. All right. So let's think through answers 11 through 15. Which extrasolar planet system has the lowest mass star? So this one is 2, this one is 1, that one is 1, that one is 1. So B, C, and D. Which extrasolar planet system has the highest mass planet? That's a 1, that's a 2, that's a 2, and that's a 1. So B and C have the highest mass planet. In which extrasolar planet system is the planet closest to the star? So A, C, and D, they're all 2D. And in case B, it's a distance of 1D. So the one where it's closest is B. All right, and we get, let's do question 14. In which extrasolar planet system A through D will receive light from the star with the largest Doppler shift? Explain your reasoning. Well, we get a larger Doppler shift for a more massive planet, a less massive star, and they are close together. So the one with the lowest mass star, B is one of those. The highest mass planet, B is one of those. And the one where they're closest together, B is the only one of those. So which one is going to have the largest Doppler shift? It's B. And which star system has the extrasolar planet that is easiest to detect from Earth? Also B. The larger the amplitude of the Doppler shift, the easier it is to detect. If the Doppler shift corresponding to the induced motion of the planet induces on the star is too small in amplitude, you just won't be able to detect it. All right, let's visit with our two students, 1 and 2. Student 1, I think extrasolar planet system C shows the star with the largest Doppler shift. This is because the star in system C has the largest orbit. This means that the extrasolar planet will be easiest to detect. Student 2, I don't think that the Doppler shift is caused by the size of the star's orbit. To cause a large Doppler shift, you want a low mass star close to a large mass planet, and that is extraplanet system B. So again, they are staying to form. Student 2 is correct, and student 1 is not. It is not the size of the orbit. It is this combination of you want a low mass star, a large mass planet, and they are close together. That is the direction of having an easier to detect planet because it has a larger Doppler shift. All right, I'm going to do something a little challenging here. We're going to match up radial velocity curves with those 4 extrasolar planetary systems. So figure 4 below shows the graph of our 4 radial velocity curves, E through H, for the 4 stars in figure 3. Use these graphs to answer questions 17 and 18. Okay, so just go through which one has the biggest Doppler shift is going to be F. Next biggest amplitude of the Doppler shift is graph G, then graph E, and lastly H. All right, so let's go through and match these up. Match each graph E through H with the extrasolar planet systems A through D from figure 3 and explain your reasoning. So let's start with the tallest of allest. The one that had the largest Doppler shift was the one where we had the most massive planet with the least massive star in the smallest orbit. That gives us the biggest Doppler shift. That's case B, and that is graph F. All right. The next strongest Doppler shift, they're all the same distance away, but in case C, I have the more massive planet. And this should be the one with the next highest amplitude of Doppler shift. So we go through and look at our graphs of Doppler shift. So extrasolar planet system C is going to correspond to graph G for the radial velocity curve. All right, so I'm taking care of this one, taking care of this one. Let's look at the 2 that are left. They both have the same size orbit. They both have the same massive planet. In case D, I have a 1 M star, and in case A, I have a 2 M star. And we'll get a larger Doppler shift for having the lower mass star. So the next highest Doppler shift is going to be in case D, and that corresponds to graph E. That means the one with the smallest Doppler shift, which is the amplitude in graph H, corresponds to system A. All right, so make sure that ranking compared between your amplitudes when we just have like a picture for what the motion is going to be and what the actual radial velocity curves look like and how they match up. So make sure that makes sense. All right, question 18. On the graph, E, F, G, or H that depicts the largest Doppler shift, we want to draw a circle on the curve at each time that corresponds with the star moving with the fastest speed toward Earth. So a circle on the curve at each time that corresponds with the star moving with the fastest speed toward Earth. So that is a blue shift, and moving towards us means you have the smallest velocity. So I'm going to draw circles for each of those. All right, next question. Draw a triangle on the curve at each time that corresponds with the extrasolar planet moving with the fastest speed toward the Earth. So extrasolar planet toward the Earth, that happens because they move in opposite directions. When star moving fastest away from Earth. So that's the biggest red shift, or the greatest positive radial velocity. So at the top of all of these curves, draw in a little triangle. So the triangles are when the star is moving the fastest away from Earth, which is when the extrasolar planet is moving the fastest towards Earth. All right, last question, which is in reference to figure 5. Given the location marked with the dot on the star's radial velocity curve, at which location I through L, so I, J, K, L, would you expect the planet to be located at this time? Explain your reasoning. Okay, so we're seeing radial velocity curve for the motion of the star. So let's just fill these in. So we try to make sense out of this. And they're on opposite sides. So planet at J is the star at J, planet at L, star at L, planet at I and star at I, planet in K, star at K. Okay, we are going from seeing at this point the star is moving the fastest away from Earth, so this has to be I, and here is the fastest where the star is moving towards Earth, and that has to be at K. So there's K. All right, as the star is moving around, we're going from I to K, going from I to K, and the point where there's 0 Doppler shift is where L is. So this is